Hi Crisis, I'm in my car today. There's a lorry in front of me. Would you ever believe if I said that? The distance between this lorry and me is 10 meters, but if I was moving towards this lorry, the distance would have been less than 10 meters with respect to me. If not, hang on for a while. The justification is coming up right now. If you're wondering how this happens due to the length contraction, which is one of the main topics in special theory of relativity. But the basics of the special theory of relativity has been already explained in my previous video, which is the first episode of this video series. If you have not watched this video yet, I invite you to watch the very first part of this video, which is very, very important. The prerequisite knowledge is there in the first episode of this video series. Right. And the next important thing is that length contraction. If you really want to understand the length contraction, you know how time dilation works in advance. If you have no idea how time dilation works yet, it's there in my first part of the video series, which is in the first episode of this video series. The video link is there on the description, so you can find it out and watch the very first part of this video series in advance. Right. And the next thing is, if you really want to understand the length contraction properly, there are various methods. Various experimental evidences show that the length contraction is true, and even the mathematical relationships that we can use to prove how length contraction works. But I think the most convenient method here and the most convenient technique, experimental technique that we can refer to is the muon decay experiment. I think that is the most favorable technique for us to understand the length contraction really well. Right, the muon particles, they decay instantly, guys, because the muon particles are very unstable. If you really don't know what muon particles are, muon particle is a fundamental particle that we meet in particle model. It's a lepton, but it's a very unstable lepton, unlike electrons. The average lifespan of a muon particle is something around 2.2 microseconds, and most of the time they exist at the upper atmosphere. The gap between the upper atmosphere and the Earth's surface is it's an average value. This is not the exact value, but this average value is something around 10 kilometers to 6 kilometers. It varies something around 6 kilometers and 10 kilometers. We can't say the exact value, but according to the classical mechanics or classical predictions, the muon particles within its lifespan, they would never reach the surface of the Earth. Surprisingly, now I'm going to show you with a proper calculation that muon particle would never be able to reach the Earth's surface within the lifespan. But surprisingly, the prediction of the scientists went wrong, as so many muon particles can even be detected at the sea level. If you really want to understand what's going on here, it's better to make use of math. As you can see here, the blue color circles represent the muon particles, which are at upper atmosphere. And at sea level, there's a person who's at rest observing the muon particles. And right now, with respect to the observer, I'm going to measure with classical mechanics. With the assistance of the classical mechanics, I'm going to find how far these muon particles can travel from upper atmosphere. Right, we already know that the most simple equations that you can use, which is S equals ut, is one of the easiest equations to find the distance, as they are moving at this constant speed. There's no acceleration. So the distance traveled by a muon particle under this circumstance is now speed is almost 2.98 times 10 to the power 8 meters per second. So I put the values 8 times 10 to the power 8 times, yeah, the average lifespan within its average lifespan, right? So otherwise it will decay into something else. So therefore, it is no longer a muon particle. So if you really want to observe it as it is, as a muon particle, you have to detect it within its lifespan, right? So now 2.98 times 10 to the power 8 times the real lifespan, or the average lifespan, is 2.2 times 10 to the power minus 6. Let me check the value. Now this value is almost equal to 655.8 meters, something around 600 meters or 700 meters, but still this value is even less than 1 kilometers, right? So then, according to the classical arguments, the distance that a moving muon particle can travel before decaying it is something around 650 meters. Right. Now, can you see there is a loophole here that does something missing here? Why? Because the classical physics is not sufficient, guys. It's insufficient to explain this observation. So that's what I'm going to show you now. Now, let's apply these things into our favorite special theory of relativity. Right now, the time dilation is going to play a role here. Okay, now with respect to the observer at rest here, right, we already know that the time is a bit slower for the moving observer, right? So we already know that when there's a moving observer, for the moving observer, the clock is ticking bit slowly than the rest observer, right? So which means now when right, if you take that t is the, or t naught is the real lifespan of the muon particle, this time is experienced by the muon particle. So this is the real lifespan of the muon particle, right? So let me consider it as the lifespan. Actually, this is an average lifespan of a muon particle. But is it still be same, is it still same for the rest observer? That's my question here. We already know that even if t naught is the lifespan of the muon particle, with respect to the rest observer, this time is supposed to be something greater than this t naught, right? We already know that the clock is ticking bit slowly for the moving particle or for the moving frame. So therefore the same time experienced by the rest observer should be greater than this time, right? So let's apply it into the equation that we already know, because we already know the t is the the same lifespan, but with respect to the lifespan of muon with respect to the rest observer. Right, now let me find how much that value is. We already know the equation. The t equals to t naught and 1 minus v squared over c squared, the total square root. Right, let me put the values. The t naught is the real lifespan experienced by the moving muon particle, and here now 1 minus v squared. The v is the speed of a muon particle, is very close to speed of light. Those are relativistic speeds. 10 to the power 8 squared over 3 times 10 to the power 8 and the square of it, and take the root of this. Now if you find out this value, you end up having 19.1 microsecond. Now this is going to be really interesting, because the lifespan with respect to us, as we are the rest observers with respect to the muon particle, is 19.1 microsecond. It's not 2.2 microseconds, right? Let me continue. Okay, now let's apply s equals ut with respect to the rest observer, right? So s is the distance, that is distance, and u is the speed of the muon particle, which is already known, 2.98 times 10 to the power 8 times 19.1 microseconds. Right, now can you see that the distance traveled by the muon particle with respective to the rest observer is sorry, my bad, it's 5,691 meters, which is almost equal to 6 kilometers. Now can you see that with respective to this rest observer, which means the stationary observer at the sea level, this muon particle still has an ability to reach the sea level, right? So that's why still we can detect these muon particles even at the sea level, right? That is not the most interesting thing here, right? But I have got another question now. Imagine instead of a muon particle, now this is my upper atmosphere again, right? Now there's another person, another observer moving, right, from upper atmosphere to the sea level, and this is my person who's moving at the same speed, 2.98. It's impossible to happen, we already know that, but just for sake of this calculation, 2.98 times 10 to the power 8 meters per second, right? Now there's a rest observer, as I mentioned earlier, there's a rest observer here. Yeah, now imagine this is your friend, the yellow color friend is moving towards the orange color friend is waiting to see him, right? Now there's a little problem that I'm going to show you right now with respective to the rest observer. He knows that the real time of, not the real time, I don't like to use the real term, but with respective to him the lifespan is 19.1 microseconds. So therefore it can travel these 6 kilometers. It's not a problem, it doesn't matter. But with respective to the moving observer or his friend, still he experiences the same 2.2 microsecond as its lifespan. So how could he travel this distance within this, I mean 6 kilometers within this 2.2 microsecond, which means this shows that with respective to this moving observer, guys, it is no longer 6 kilometers, which means now if he feels that, if the guy who's at rest feels that the distance that the object or his friend has to travel is 6 kilometers, for the moving observer, actually it is not 6 kilometers anymore, it has to be something lower than that, but he doesn't even know that is real, right? He feels that, sorry, he doesn't even feel that is something something wrong, or it's not actually wrong, but what he observes is that he still feels that he travels in this time 655 meters, right? That is, so which means now according to, or with respective to the yellow color observer, he feels that his friend is there 655 meters away from him. But same scenario, same observation, but two different ways of observing it. That is what I wanted to tell you guys. Right now, now mathematically, I'm going to make an argument again. Now let me take that h is the now 6 kilometers. I'm not going to use these numbers anymore. Right? Imagine h naught is the real distance, or the distance it travels with respective to the rest observer. H naught, the distance travel with respective to the rest observer. Right, and on the other side, but h is the distance it travels with respective to this moving observer, the distance traveled with respective to the moving observer, right? Okay, but speed should still be the same for both of these observers, guys. So speed cannot change, right? So therefore I can say that the h naught over, right, h naught over, we already know that h naught is the distance traveled with respective to the stationary observer, and with respect to him, the time it takes to travel this distance is simple t. Simple t has already been introduced previously, right? The simple t is the time lifespan of a muon particle with respect to the observer. This time it's not muon particle. The muon particle is replaced by the person, right? So, but on the other side, h is the distance traveled with respect to the moving observer, but as he feels, the distance is, sorry, the time is not t, that is t naught, because that's the real time, the real, I mean, the real lifespan of the muon particle, right? So let me put my previous calculations or previous relationships, and h naught over t is not t, we can put it as t naught 1 minus v squared over c squared square root, and let me take that the speed of this one is not 2.98. I'm going to take it as v now, right, is equal to, on the other side, h over t naught, right? Now finally I can make a relationship now. So h naught 1 minus v squared over c squared square root over t naught is equal to h over t naught. I can cancel out this t naught to t naught, right? I end up having a nice relationship now. The relationship is h naught 1 minus v squared over c squared square root is equal to h, right? Now you can clearly see that the distance traveled with respect to the rest observer, if you measure, now imagine if you're the rest observer now, the distance measured by yourself is h naught, is equal to h naught here, but for the moving observer it is not that value anymore, it is simple h, and you can correct it by using this formula that I have just derived to find the distance that object or your friend, if your friend is traveling towards you, with respect to his frame, the distance traveled by him can be calculated using this very important relationship, guys. So this is ultimately called the length contraction, and this is the second part of the special theory of relativity. That's all about my justification, guys. See how speed can change things? Thank you for watching my video. See you with the next episode of Special Theory of Relativity.